Okay, in this video we're going to have a look at SUVAT still, but also including a little bit about gravity and the rate of acceleration due to gravity. And I'm actually going to play you a short clip. I'll provide a link to this on the SharePoint site as well, but I am going to play it within this video as well. It's just quite a nice introduction to it.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems, and that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of, so they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So, in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCV 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
Exactly. They came down exactly the same. Wow.
Look.
Watch right there. Look at how they hit right there.
Exactly.
You're back on the side.
Exactly the same.
Feathers don't move, nothing. Look at
that. That's just brilliant. Isaac Newton would say that the ball and the feather fall because there's a force pulling them down, gravity. But Einstein imagined the scene very differently. The happiest thought of his life was this: the reason the bowling ball and the feather fall together is because they're not falling. They're standing still. There is no force acting on them at all. He reasoned that if you couldn't see the background, there'd be no way of knowing that the ball and the feathers were being accelerated towards the Earth.
Okay, I quite like that video. Don't worry too much about the end bit about relativity. We don't really touch on relativity in A-level maths. You have to go and do A-level physics for that. But the important thing is that without air resistance, they fall at the same rate. Okay. So if we've got air resistance, then obviously they fall at a different rate. We saw that with a feather and bowling ball, and you see that in your everyday life. That's fine. But without air resistance, which most of the time in A-level mechanics we choose not to model, just to make it simpler, things will fall at the same rate. And that rate is the acceleration due to gravity and we call that g, which is a constant. So sometimes we'll just write the letter g, but we use the number 9.8 meters per second squared. Okay. Where this number comes from, again, you'd probably have to do a bit more A-level physics to do that, but Isaac Newton had an equation to do with the gravitational force between two objects. You can use F equals G, which again is a different constant. It's not the 9.8, it's a different one. But Gm over r squared was his equation that he used to calculate the gravitational force between objects. And actually, if you use the value of G, this constant G, and the two masses, then you can calculate that the acceleration is 9.8 meters per second squared, but that's more of a physicsy thing. What's important for us is they fall at the same rate, 9.8. So let's look at a few examples of how we can use this in the context of some mechanics problems. So, a book falls off the top shelf of a bookcase. The shelf is 1.4 meters above a wooden floor, so it's got to fall this far. Find the time it takes to reach the floor and the speed at which it strikes the floor. Now, if it falls off the top shelf of a bookcase, we can assume that u is 0 because we're dropping it. We're not throwing it at the floor, we're just dropping it. So u is 0, and a is going to be 9.8. So we've got s, we've got u, we've got a, and we want to find t. So we can use s equals ut plus half at squared. So 1.4 equals 0t, so that's just 0, plus half a, so that's going to be half of 9.8, times t squared. And then we can solve that to find t. So it gives me 0.53 seconds it takes to hit the floor. Now, in real life, it would take slightly longer than that because we've assumed there's no air resistance, but for now, that's good enough for us. Part B, the speed with which it strikes the floor. So now we're looking to find v. Okay, but all the other variables are the same. So I think we can use v squared equals u squared plus 2as. So it's going to be 0 plus 2 times 9.8 times 1.4. And we can find v. And the speed it hits the floor at is 5.24 meters per second. Okay, so having this value for gravity is really useful when we've got objects falling through the air. Okay, let's have a look at this other one. Okay, a ball is projected vertically upwards from a point x, which is 7 meters above the ground, with speed 21 meters per second. Find the greatest height above the ground reached by the ball and the time of flight of the ball. Let's just draw a diagram then. So here's the floor, and here's this platform that it's being launched off of. Okay, and it's at 7 meters above the ground. And it's being launched, so it's going to fall back down like that. That's going to be a sort of flight path. Okay. Now it's projected vertically upwards with speed 21. So u equals 21. And we want to find the greatest height. So we want to find this point here. Okay. Now, like we talked about in the last video, that point at the top is where it's turning around. So where it's going from moving upwards to where it's moving downwards. So it's got a positive velocity on the way up, and on the way down, it's got a negative velocity. So that must mean at the top, its velocity is 0. So we can use u equals 21, v equals 0. I want to find the height, so that's going to be s. Now the other thing I know is the acceleration due to gravity, but because it's been launched with 21, and as it gets higher in the air, it's actually slowing down, isn't it? To the point where, when it's at its peak, just for a split second, it's got a velocity of 0. So because it's slowing down, I'm going to label its acceleration as minus 9.8. Okay, and gravity is pulling it downwards is another way to think of that, and downwards would be a negative direction. Well, now we've got these, I can use v squared equals u squared plus 2as. We can find the displacement s. So you've got 21 squared divided by 2 divided by 9.8. So that's 22.5 meters. Now, that was measured above where it started. So actually that 22.5 is that distance there. So 22.5. So above the ground, that's going to be 22.5 plus 7, so 29.5 meters above the ground. Okay. For part B, the time of flight of the ball. So we want to find how long does it take to go from here all the way up to the top and then all the way back down. Okay. Now there's two ways we could do this. We could find maybe how long it takes to get to the top and then find how long it takes to go from the top to the bottom. But we can actually do it in one step, and I think it's a bit more elegant if we do it in one step. Now the way that we do this is we consider all the other variables we've got already. So its initial speed is 21, acceleration is minus 9.8. Okay, it's important as well to understand that it's always minus 9.8 because it's going upwards, but it's being pulled back down. So gravity is acting downwards, so it's minus 9.8. And when it's on the way back down, even though it's getting faster, its acceleration is still minus 9.8 because it's accelerating downwards. It's accelerating back towards the ground, so it's still a negative value for the acceleration. Okay, so that applies for the whole journey. I'm trying to find the length of time. The other thing we know is that this point here is we know its location, or we know its displacement. If this point here was the start, this would be displacement 0. We worked out that the peak was displacement 22.5. If we get to here again this would be displacement 0 because it's at the same height that it started at. So when we're down here, the displacement here is going to be s equals minus 7 meters because it's 7 meters below where it started. Okay, and now I can use s equals ut plus half at squared again. Okay, so I've got s is minus 7, u is 21, half a is minus 4.9. Now I've just got a quadratic to solve, and again I'm just going to use my calculator to solve this. So I've got two times. The first time is 4.6 seconds. The other solution I get is t equals minus 0.31. Now obviously it's the 4.6 that we want, but it does have some significance, this minus 0.31. Obviously we're not really after a negative time, but if I kept this trajectory going sort of before it started, so if I followed this parabola down to the ground here, then it would be this point here that it's talking about. So it's basically saying when else might it have had a displacement of 0. So it's sort of a, I guess like a virtual solution there, but we're not really interested in that one. Okay. All right, example 3. So a particle is projected vertically upwards from a point O with speed u. The greatest height reached by the particle is 62.5 meters above O. Okay. So here's the ground. It doesn't say it's on a platform this time. I think it's just this sort of thing. It's launched upwards with speed u. The greatest height, so that's up here, is 62.5 meters. Find the value of u. Okay, so we know that the initial speed is u. We know the greatest displacement is 62.5. The other thing we know, remember, about the peak is that the velocity up here is 0 because it's going from moving upwards to moving downwards. So in between it must have a velocity of 0. So you can use that. And the other thing we know is gravity. And again, it's been launched, but then it's slowing down as it reaches the peak. So A is minus 9.8. And now we can use v squared equals u squared plus 2as to solve this. So you get 35 meters per second. Part B, find the total time for which it is 50 meters or more above O. Okay, well the maximum height was 62.5, so maybe let's put 50 at about here. Okay, it would also be obviously about here. So what we're trying to find is how long is it above 50 meters? So how long does this section here take? Okay. Now again, let's think about the displacement of this. So we're looking for the two times, so this time here and this time here, when it reaches a displacement of 50 meters, and then we can just find the difference between the two times. And that'll tell us how long it's been above it for. So we're looking for a displacement of 50 meters. U was 35, A is minus 9.8, and we want to find T. So we can use S equals UT plus half AT squared. Okay, and then we can solve this quadratic. So my two times are 5.17. The other time is 1.97. Okay, so those are the two times when it is at a height of 50 meters. So presumably this first one is 1.97 seconds, and then it takes until 5.17 seconds to be here at this height again. So the difference in time, the time that it is above 50 meters, is the difference between those two, which is 3.2 seconds. Okay. What we're doing algebraically here is we're basically finding the intersection of a curve and a straight line. So we're finding the intersection of the line, S equals 35t minus 4.9 squared, sorry, 4.9t squared, which is just ut minus half at squared. That's basically the equation of trajectory for this particle. And we're finding when does that intersect the line S equals 50. And we're finding when those two lines intersect each other. A bit like we do in pure maths with graphs and so on. Okay, last one. Okay, this one's got a bit more going on. A ball A falls vertically from rest at the top of a tower which is 63 meters high. At the same time as A begins to fall, another ball B is projected upwards from the bottom of the tower with speed 21 meters a second. And they collide. Find out the distance of the point where they collide from the bottom of the tower. So let's start with a diagram. Okay, so here's my tower, and its total height is 63 meters tall. Then we've got ball A, which was dropped off the top, and it was falls from rest, so you can say that u is 0 there. Now we've got ball B, which was launched upwards with speed at 21 meters per second. And obviously they collide somewhere here. Okay. And what we're looking for is that distance there. How far off the floor do they collide? Okay. There's a couple of ways you can approach this problem. In fact, there's quite a few different methods for it. But I'm going to show you what I would do. I'm basically going to make an equation for the displacement of both of these particles. And then I'm going to set them equal to each other. Because that's what I want to find is when are these two particles in the same place? When do they meet? I'm actually going to start with particle B because I think it's slightly easier to think about. So for particle B, I'm going to use S equals ut plus half at squared to model its motion, just like we did for the last projectile question. So its displacement off the ground, which is S, is going to be ut, so that's 21t, half a, well, it's being projected up, so it's going to slow down, so its acceleration is minus 9.8. So that's going to be minus 4.9, because it's half a, t squared. Okay, so this is like an equation for where b is at any point in time. So when t is 0, it would be at 0. When t is 1, it would be 21 minus 4.9, that distance off the ground, and so on. If I now do the same thing for particle A, that one's falling, so u is 0, so it's not going to have the ut in there, that's just 0. It's still going to have minus 4.9 t squared though, because it's still falling down towards the ground. In a downwards direction, it's still negative. Basically, my diagram is set up so that up is positive and down is negative. So it's accelerating, it's getting faster and faster towards the floor, so therefore it's got a negative acceleration. Now, the only problem with this is I need to take into account the fact it starts from the top. Because otherwise, when t is 0, so at the start, this would give me a height of 0, which isn't true. It starts at 63 meters, so I'm just going to add on 63. Okay, because then when t is 0, it starts at a height of 63. When t is 1 second, it will be 63 minus 4.9 meters, so it'll be a bit lower than that, and so on. So we've got these two equations which model the position of B and the position of A. Now I'm going to set them equal to each other because I want to find where do they meet, where do the balls collide. Okay, and then I can solve this to just get t equals 3. So they collide after 3 seconds. Okay, well that tells me when they collided. I want to know where did they collide now, and I want it to be the distance off the bottom. The distance off the bottom is modelled by the displacement of B, so I'm just going to use this one here. So B was 21t minus 4.9t squared, and we know now that t is 3. And if I do that, then I get 63 minus 44.1, which is 18.9 meters above the ground. Okay. There are some alternative methods you can use for this question. I think that one's probably my favorite just because it means that you have a consistent system for both particles. But there are other ways, and if you look in the textbook in this chapter, you will find this example, and you'll find some slightly different methods how to do it too. Okay. So questions you can do on this, for example, exercise 9e. That's based on Suvat of gravity, or you might want to have a go at mixed exercise 9, which is obviously a mixture of questions from this chapter, which includes things like ST graphs and VT graphs as well.